Hey, everybody said, thank you, Salman, for giving the presentation in the morning. And really, I would like to share, I won't bore all the students with the data. So what we do, I will summarize in one slide, but email me or any question you have. And I'm a professor in pharmacology and regenerative medicine, and we do a lot of projects and collaborates with a lot of people in the both biomedical engineering as well as in College of Medical College of Medical, whatever, yeah. So what we do, so my basic uh, favorite organ is the lung. So right now you are sitting, you are laughing, you are smiling. It is because your lung is cooperating with you. You can breathe. So these are the alveoli in the lung that do the gas exchange, right? So here is your tiny, tiny alveoli, balloon-like. It's kind of when you are breathing, they expand, and when you exhale, they constrict, right? So we work on lung injury. And why we work on lung injury? Because you have felt over the COVID SARS disease killed millions of people all over the world, right? So you want to understand what is the mechanism that lung injury develops, and can we resolve that lung injury? Because if we can resolve, we could have saved a lot of lives in the world, right? And another disease I work is the lung cancer. So how the cancer, solid cancer metastasize in the lung, what is the mechanism there? So in doing so, if you see the lung, it's a mesh of there are about 56 different type of cells in the lung. And the more common cell we work on is the alveoli, balloon, as I mentioned. They are made up of endothelial cells and epithelial cell mainly. So if you see, there are very minute gap between, if you like engineers, you can see how much surface tension is between the endothelial cell and epithelial cell, and how much air they are having in each of these small balloon, right? So what we do is that how these endothelial cell talk to your epithelial cell, and in turn, they talk to the immune cell. So if you are sitting here, every pathogen, every pollutant goes into your lung, right? So how these immune cells interact with these pathogens and how you can get rid of them. So this is the function of all your endothelial cell and immune cells. So first I work on the inflammation, how they interact, how we can promote the resolution. And now when your lung is breathing, right? So it's process of breathing, your lung is stretching, combating back. So that's called mechanotransduction. So we are trying to understand how the endothelial transduction within the endothelial cells transform the epithelial cell communication or immune cell communication. We also work with the matrix-derived androgel from the lung itself, and that work is done in collaboration with Dr. Naba, who will be presenting next. So she has told us how to actually isolate this extracellular matrix. And then we have gone further. What is the rigidity of these matrix? What they do in a normal cell. So if you take out the matrices from the normal mouse or versus a disease mouse, how they transform your cell signaling, right? So that's what we are trying to understand. And then we work on the tumor microenvironment and metastasis I mentioned. So what we do is we are focused on the lung cancer, and then we put the lung cancer cell and we watch where they go, how they metastasize. Can we inhibit a gene, and can we stop their migration into the lung? So that is the process of microimmunity. And then we also in the process, because we are working on this, you got to have some kind of a nodal switch, but a central piece of signal that seems to be controlling most of the phenomena in the cell. So we have been able to form the cell-based and peptide-based therapeutics. So we have been able to devise the small molecule inhibitors or cell-based therapy such as alveolar macrophages. If you put back good macrophages, would you be able to normalize the mouse lung, or you would be, if you put back the endothelial cell into the disease mouse, would you be able to restore their lung fluid homeostasis? And in doing so, we do have to identify what cell are good cell, what cell are bad cell. Can we make the good cell bad cell? So this is done using the single cell RNA-seq, and we do bioinformatics, which you guys may have more capability of doing it, and in which we define how many clusters are bad, what's the genomics of that, and what is the what is the translation machinery that is controlling, or transcription machinery that is controlling that. So this is all different kind of projects going on in the lab. So what we do in the lab, so these are the tools we use. So we use a lot of cells, as I mentioned. These are immune cells, neutrophils, endothelial cell-specific knockout, as Salman mentioned. So basic is that you need to delete a gene to understand its function, right? So if you have a normal scenario, what happens when you take out the gene? Is it a bad gene or is it a good gene? And how does it affect the lung function? And then we do a lot of editing of the gene, and gene delivery is our favorite because we can put back normal gene or the bad gene to recapitulate the disease process in the mouse, transcriptomics, and in doing so, defining the flow cytometry, peptide, and hydrogel. And this is my lab, and most of my students have been going to the academics, one professor, NIH grants, as well as industry, and also in teaching institutions. So there's a mixed bag of students which I have trained, and they have been very, very successful. With all, I will be stopping here and looking forward to have you join the lab and shoot me any question you have. Thank you. Bye-bye.